This is the first of two videos about encoding knots by strings of numbers so that you can insert the data, input the data into a computer, which could be useful for computing Jones polynomials and that sort of thing. So let me first of all tell you about the so-called DT code, named after Dowker and Thistlethwaite. Dowker was a Canadian topologist. Thistlethwaite is a knot theorist who studied in the UK and is now in Tennessee, I think, was also a pianist at one point. So the DT code is formed by taking a knot diagram. It's really the code of a knot diagram, and starting somewhere in a given direction, going round the circuit and labeling the crossings. Now, each crossing is covered twice. You go over it and under it in one order or the other, so it will have two integers associated to it. So if there are C crossings, you'll end up by using 2C labels, and you use these successively. So you'll go up to 2C and then you start again. We're not interested in what happens when you start again. So let me give you an example of this. So let me draw a trefoil knot. Try and draw a trefoil knot. That's a trefoil knot. Now, I'm not really interested whether we take a knot or its mirror image, because unfortunately this code doesn't distinguish the two, but it will be important to make that choice to actually start somewhere. So let's suppose that this is the right-hand trefoil knot, so that means that the overpasses will look like this. You know you've got a trefoil if you have just three crossings and they're alternating, then it must be either a left or right-hand trefoil. So we choose somewhere to start, and we choose somewhere to start away from a crossing, but we choose a direction in which our first encounter with the crossing will be an underpass. So if I start there and move round sort of in this anti-clockwise direction, I'm going to label each crossing with two integers. So first of all, I have a 1, then I have a 2, and then I keep going round. I always like to put my labels sort of on the right as I arrive. It's just my own convention. So 3 there, and then we come back to this crossing that we've gone under before, but this time we're going over it and it gets labelled with a 4, and then we get a 5, and then finally we get a 6 coming round here, and then we go back to 1. So what you do with these integers, you see what's happened here is that we've actually, each crossing has been labelled with an odd integer. All the underpasses are actually odd because this is an alternating diagram and we started with an underpass. It follows that all the underpasses will correspond to an odd integer, and the overpasses will correspond to an even integer. So what's happened here is that we started really with if we look at the odd integers, each of these corresponds to an even integer, but not in the obvious way. 1 corresponds to 4, 3 corresponds to 6, and 5 corresponds to 2, because what's going on here is that these columns, each one represents a crossing, and the two labels assigned to that crossing. But because to sort of encode this information, we don't need the top line in which I just put the odd integers in order. We just need to know what the even numbers are in the correct order. So the code in this case, the so-called DT code, would be 462. I prefer to put commas because eventually we'll have more than one digit, but most people just leave gaps and we don't normally put brackets. So that is the DT code of this trefoil diagram. Of course, you could represent a trefoil with 4 crossings or more, and then you'll get a different looking code. But if you stick to 3 crossings, at least in this case, this is what we get. So let me just explain that in writing, what I've just said. So I'm just beginning with an alternating diagram. It's not hard to modify the procedure. If we have an alternating diagram, then and we start with an underpass, then the underpasses will correspond to the odd numbers, as I said, and the overpasses to the even numbers. So what's going on? Each crossing, the set of crossings will therefore define a bijection from the set of odd numbers to the set of even numbers up to 2c. So there will be 2c. We'll have the even numbers from 2 up to 2c if there are 2c crossings, if there are c crossings. And then the code is just a list of the even numbers in order, the images of 1, 3, 5, 7, those even numbers. That is the DT code, the Dowker-Thistlethwaite code of the knot. And so, in other words, if we want to ask what sort of codes can we have if we have C crossings, well, it's all possible. We could look at all possible permutations of the first C even numbers. But many of those, every one will actually give rise to a valid knot diagram. Although many of those diagrams won't be terribly useful. Some may be unknots, many will be unknots, and so on. So, in fact, if we start with a knot, we'll get a particular code, and we may be able to get different codes representing the same knot diagram. But there will be many other permutations. Most other permutations of those even integers will not represent the knot we're interested in. And then I'll explain with an example how to modify this method for non-alternating diagrams. It's very straightforward. So let me talk again about the Trefoil knot. I've already shown you the code 462, but let me try and reconstruct it by code. Pretend we didn't know what the Trefoil knot looks like, but we know the procedure of the DT code, and we try and reconstruct the knot from the code. Well, this is an easy exercise. Well, it's a sort of interesting exercise to do. So we start with a little arc that's going to bring us to our first crossing, which is labelled number 1. So remember, the 4 corresponds to 1, the 6 corresponds to 3 in our bijection, and the 2 corresponds to 5. So 1 is overpassed by an arc, so we come up to crossing which is labelled number 1, and it goes under an arc which eventually will be labelled 4. Well, the crossing will be labelled 4, I should say. So I just put a 4 at the top for the moment. And then we go on to label number 2, crossing with label number 2. And that arises as an overpass of some arc in which the same crossing, will be labelled number 5. So I put a 5 sort of lurking around here. Then we go on to 3. Crossing number 3, which will be coming as an underpass, and 3 corresponds to 6. But then what happens, you see? Well, then what happens is that 3 has to go to 4. Well, I put my 4 at the top, so maybe I should go around the top to get to that. So it goes like that. But I prefer to put the 4 now down here, so it's in the sort of correct position. So 3 goes to 4. And then 4 goes, obviously after 4 we have 5, but the only way I can manage that is to connect these two. And so the 5, I forgot to put the 2 there, the 5 ought to go there really, because I always like it on the right as I arrive. And then after 5 we have 6, unusual statement. And you see, it's sort of miraculous that it works out that I didn't get stuck here. I had an arc coming out as 5, and I had exactly one I could join it to underneath the other arc. And that all worked out rather nicely. And then after 6, we're coming back to 1. So we just go around here and come back to 1. And I've completed the diagram. And this must be the Trefoil knot, because we're going, we have a knot with 3 crossings. We're going, if we go along here, we're going under, over, under, so it's an alternating knot, and therefore it must be a Trefoil knot. You could also make it sort of on a sort of square lattice. You could make it all with sharp corners and get an even sort of neater representation of the Trefoil knot. But the question is it the right one or the left one in this particular diagram? It must be one or the other. Now you might guess there that it's the you might say, well, it must be the right one, because if I look at this crossing here, the underpass is sort of veering. As I come outside, it's veering to the right. It's veering to the left. Sorry, so you might guess this is the left. This is the left trefoil knot. That would be a reasonable guess. This is an error I actually got wrong in my first introductory lecture. The problem is that this is not the standard diagram of the trefoil knot, and you can see that because there are only 2 arcs on the outside, whereas the usual diagram would have 3 arcs on the outside. So one way to remedy that would be to simply rearrange things so that one of these arcs, for example, I think the last one I did, I went around the bottom, but I could have actually gotten around the top to connect it there. Had I done that, obviously it's quite a legitimate way to draw it, that's fine, but that would have been the more usual, actually. Though it looks strange, it would have been the more usual trefoil diagram, because this time I've got exactly 3 arcs on the outside. One, they need to be sort of deformed a bit to make it more symmetrical looking, but I've got 1, 2, 3 arcs on the outside. And then if I look at my crossings going out, you see it's actually if you look at this crossing here, or any of them, or the same one as before, it's actually the underpass is going right as I look at it. So it's actually it's not the left trefoil knot, it's actually the right trefoil. On the other hand, I could have got the left trefoil knot by, at the earlier stage in which I decided to join the 1 to the 4, because I put a 4, I had already written a 4 at the top. I could have actually not done that. I could have gone this way instead, and then had it like this and done it differently, and that would have given me the left trefoil. Anyway, that's the idea of how you reconstruct a knot from the code, and this is the simplest example really, but you can you can have fun with other slightly more complicated examples. It takes a bit of practice to get it right. So let me go backwards again. So here's the figure 8. This is the usual diagram of the figure 8 knot with 4 crossings. We know that this is equivalent to its mirror image, so we don't have to worry about mirror images here. But what would its DT code be? Well, I have to start somewhere. So there's a lot of space around here. So let me start here, and I want the first crossing to be an underpass, so I go in this direction. Let me just do it more quickly this time. So it's 1, 2, 3, 4, 5, 6. Well, it's wrong side, isn't it? I go around and put the 6 there. I'll put the 6 there. 7, 8 here, not much space. Going round 7, 6, 7. Get stuck. 5, 6, 7, 8. What I'm wrong. Start again. 1, 2, 3, 4, 5. Going round this way. 6. Continuing this way. 7, 8. And going round. Oh, of course, I was going to put a 9, but I've got back to where I started with because there are only 4 crossings. That's what I was doing wrong. So that's fine. That's correct. And what is the DT code? Well, 1 corresponds to 6, 3 corresponds to 8, 2 corresponds to 5, and 7 corresponds to 7. So 1, 3, 5, 7 is mapped to 6, 8, 2, 4. So it's that code there. However, had I started had I gone the other way round, I need to start somewhere where I get to an underpass first of all. So if I were to start again from scratch, but do it with an underpass, start going the other way round, I need to start with an underpass. So obviously I could start there if I wanted to. Then I would go 1, 2, 3, 4, 5, 6, 7, 8, and then I come back to 1. And this time the code is 1. Well, actually, it's the same one, isn't it? 1 is going the same way around. Well, that shows you it's not always the case that you could start with more complicated knots. If you start somewhere different, you normally get a different code. In this case, you get the same code wherever you start if you go in that direction. But if you go in the other direction, I've used my time up, so I won't do that. If you go in the other way round, you need to start somewhere where you start with an underpass. So if I want to go in the other way around, I could start there and go that way. You'd find that the code would be this. So you can get 2 separate codes depending which way you go. But I say with more complicated knots, you could get lots of codes depending also where you start. What I did want to say is what happens if we start with a code that's sort of artificially generated, like this one here, that's on more natural order, 2, 4, 6, 8, sort of the identity permutation, if you like. Well, it's not terribly useful. Let's see what happens. So let's just reconstruct the diagram from that code. So in that case, what happens is that I'm going to again have my sort of starting arc. The first crossing, so this corresponds to 1, 3, remember 5, 7. So this will come as a 1 and it's going to be overpassed by 2, but 2 follows 1. So the only way I can sort that out is to loop back. And then 2 comes to 3, and that's going to be overpassed by number 4. So the only way I can sort that one out is to go back, loop back to 4 like that, and then you begin to get the idea of what's going on. And then 4 goes to 5, which is going to be overpassed by 6. So that has to be looped back like that. And then 6 goes to 7. Now I should have really made that smaller, so I don't want that to interfere. 6 goes to 7, so I need a 7 here. This is now crossing number 6. But it will also be crossing number 7 because no, so I've got this, I'm jumping the gun here. 5 goes to 6, I'm now up to 7. It takes a bit of time to get used to this. I'm now up to 7. 7 goes underneath 8, but the only way I can sort that out is to link it up like that, so that's 8, and then we do go back to where we started. So actually what I've produced here, I've faithfully reproduced this code, but it turns out it's just an unknot. It's just I've got 4 twists because it's sort of 1, 2, because the crossings are labelled like this naturally 1, 2, 3, 4, 5, 6, 7, 8. We just get these 4 twists because a twist is the only way to sort out these 2 adjacent integers. So we get an unknot. This is the unknot, so this is trivial as a knot. Incidentally, there was on the exercise sheet a similar example in which we had sort of 5 loops. And I'm just telling you this just to remind you, this is of course an unknot because you can just untwist those. It's an unknot. So that's what happens in that example. I've got slightly, of course, that you can put the twist in different configurations. In fact, I did it like that. And that's the same representation of this code, but again it's just an unknot. It's just a circle with 4 twists. It's an unknot. Okay, let me give you an example now to explain how you handle non-alternating knots. So let me write down the DT code for this knot, and where were we going to start? Well, I choose a place where there's lots of space for the decision making. So I'm going to go in this direction of the orientation. So to make sure my first crossing is an underpass, so my first crossing is labelled 1, 2, 3, 4. Now, the problem here is that this is not alternating, so I've got to be a bit more careful. 1 is an underpass, that's what I want. 2 is an overpass, that's fine. 3 is an underpass, but now we'd expect if this were alternating, 4 would be an overpass, but it's not. It's coming as an underpass. So therefore we put a minus sign. We associate a minus sign to it. I sort of tend to put 4 minus, but I should have really put minus in front of the 4. So it's minus 4. And then we just keep going, no problem. 5, 6 is an overpass. Just keep aware of the over and unders now. 6, 7, going this way around, so we're going to 8 over, 9 under. Just worry about the even integers. 10 over, that's good, so to speak. 11 under. 12 under, that's bad. So it's going to be minus 12 or 12 minus because it's an underpass. But we don't lose any sleep over that. We keep going. 12 goes to 13, which goes to 14, which goes around to 15, which goes to 16, and I only had 8 crossings, so 16 is the maximum. I go back to 1. So what is the DT code? Well, it's just, you just again look at the sequence of even numbers in order. So paired, that is crossing by crossing. So 1 is paired with 6. I'm going to put commas in to make it clearer. 3 is paired with 8. 5 is paired with, if I can find it, minus 12. 7 is paired with 2. 9 is paired with 14. 11 is paired with 16, I think. And 13 is paired with minus 4. There must be a 15 somewhere, which is paired with 10. So that's the DT code of this particular knot diagram. It's a knot with, this is a minimal diagram. So it's a knot with crossing number 8. It's non-alternating, 8. And there are only 3 knots, I think, with 8 crossings. Prime knots with 8 crossings which are not alternating. This is one, and that's its DT code. The minuses tell you that there must be some sort of adjacent overpasses or underpasses. You see there are 2. They aren't all necessarily corresponding to minuses, but there is a minus 12 here, which sort of represents the fact that here we've gone under twice. Now, my last comment really is related to composite knots. So if we look at, here's a DT code for a knot with 6 crossings. And if you remember, these first 3 integers, they correspond to the trefoil knot. And what's going on here actually is that this is the code for the connect sum of 2 trefoil knots. Let me just show you. I think I can do that, and then I'll try and explain. So actually this is the code. You see, because of the problem of the mirror images, if we take composite knots, we can combine a knot with its mirror image, and so the same code in this case will actually give rise to, for example, two knots which are not mirror images of each other. So when we pass to composite knots, we can get codes that normally a given D2 code will just correspond to 1 knot and its mirror image, but that's only if the knot is a prime knot, can't be decomposed as the connect sum of 2 non-trivial knots. So in this case, you see what's going on is that, maybe I'll just show you quickly why this is the code. Let's just check that this is the code for, say, the one on the right. It's the code for both of them. Or let's say you can construct both of them from this same code. Let's look at the one on the right. I've got to be careful where I start if I want to get exactly these integers. So I've got to make sure I come to 3 crossings before I go back. So let's try and start here. I'm going in this direction, that's right. So this would be 1, this would be 2, This would be 3, and then I go round to 4. This is the usual trefoil knot so far. And I go 5, and then I go 6. But then, of course, the next one would be over here, and that would be a 7. And so I go on. But at least the first part is just like the trefoil knot. The 1 is corresponding to the 4, 2 to 3 to 6, and 4. Maybe I got this wrong actually. Probably copied it down wrong there. No, sorry about that. So that's the code. That's the code we saw before, the trefoil knot 4 sets 2. So this DT code with 6 integers represents can represent either this composite. So what is this one? Here we've got these are usual trefoil diagrams. These are both right trefoils put together. Whereas here on the right we have this one here on the far right is a right trefoil knot, but on the left it's actually a left trefoil knot. It looks as if it's a right trefoil knot, but that's because the usual diagram would have the thing like that. It's just I brought these strands back. So actually this is a left trefoil knot. And I could have also combined a left trefoil with a left trefoil, and I could also get that from the same DT code. So it's just a warning that when you have composite knots, there's a lot of ambiguity. But otherwise the code is quite effective because you can just write down such a code and reconstruct the knot. Okay, that's it for DT codes. Next time I'll be talking about things called plane diagram codes, which personally I find a bit more useful for shoving into the computer.